Okay, welcome back to your module 5. So in your unit 1 we discussed about the flexural stress. Okay, so that is the relationship of the bending moment with the stresses within the cross section. Okay, so now let's proceed to your unit 2, which is a horizontal shearing stress. So again, in your unit 1 is bending stress or flexural stress, and then for this unit 2 that is a shearing stress, and that is horizontal. So before in your unit 1, if this is the cross section, okay, let's say this is the cross section, the internal moment is being resisted by the compressive and tensile stress, or it could be tensile or compressive stress. It depends on the type of bending, if that is a positive or negative bending. So that is how it will resist, okay, the bending moment, the internal bending moment, which is experienced by that cross section. This time, okay, if there is now, and together with that bending, if there is now shear forces, you will now, and then let's say there are additional horizontal forces on the beam. So in the cross section, there will be what we call as a horizontal shearing stress, which is a shearing stress that is perpendicular. Okay, the area resisting that shearing stress is the area perpendicular to the cross section. So it means that is parallel to the beam. This is the cross section, that is the shearing stress, and that is parallel. So okay, that's why we call this one a horizontal shearing stress. So that is an additional resistance of the beam, internal resistance of the beam to withstand the internal moment and then the internal shear. So this time we have now what we call as the internal shear. Okay, so for this unit, these are your unit learning outcomes. So derive the formula for horizontal shearing stress, and then of course to compute for maximum horizontal shearing stress, which is found at the neutral axis. We will define later on, or we will describe why is it that your maximum horizontal shearing stress is found at your neutral axis. Okay, so now this is your definition for that. Okay, in a beam loaded by transverse forces acting perpendicular to the axis of the beam, not only are bending stress produced by parallel to the axis of the beam, but shearing stress also act over cross section of the beam perpendicular to the axis of the beam. Okay, let us express the intensity of this shearing stress in terms of the shearing force at the section and the properties of the cross section. So again, that is what I've explained a while ago. Together with the bending stress to resist the internal moment and internal shear, there should be an internal resistance, which is internal shear. Okay, and then one of that is your horizontal shearing stress. Uh, there are two types of shearing stress. The shearing stress that is parallel to the area of the cross section, okay, which is of course the one resisting the vertical forces, and then there is this what we call as the horizontal shearing stress, which is perpendicular to the cross section. So that is what we are going to consider right now, the horizontal shearing stress. Since of course your vertical shearing stress, that is obvious, okay, just summation of forces vertical, whatever shear experienced by that section, then the vertical shearing stress is just the shear force divided by the area. That is uniform if you are referring to the vertical shearing stress. But this horizontal shearing stress is a little bit different. Okay, so that is what we are going to establish in this discussion. So look at this. Okay, let's consider this one. I already discussed this one. What is this? These are the bending stresses. Okay, that could be tension. Okay, let's say we will consider a positive bending moment. So on top is a compression, below is a tension, and this is your neutral axis. So this is the side view of your beam. Okay, so that is cut through a section, and then we will consider here section A, and then B, and then somewhere there is compression on top, and then compression on top. Below is tension, tension. So that is what happened. Okay, and if we will try to consider the cross-sectional view, this is the dimension of that. So your beam is of width equals B. Just imagine this one, just like our derivation in your shear and moment diagram. Okay, if you try to cut somewhere here at section A, that will experience a moment M. If you will try to move a little bit within a distance dx along your length, then there will be an additional small moment. Okay, it could be an additional or it could be a reduction, but there will be a change which is small moment due to moving within this differential distance or small distance. So at this section you have a moment, and then moving a little bit you will have a change in the moment. Okay, that could be a positive or negative. It depends on the type of loading. So what does that mean? Due to the distance dx, there will be a small differential moment, change in moment. Okay, so again, that is what happened in this movement of cross section. Now let's continue. So if y is measured upward, okay, let's say that y there is measured upward from the neutral axis. That is just an assumption, but of course, later on your y could be going down or up. Okay, depends. So then the bending at the left section AE is given by this one. Okay, so we already established this one in your flexural stress. The stress is equal to my over I. Okay, so whatever, since we are considering that AA, section A, the moment there is M, so the stress somewhere at the point or the fiber that we are considering is my over I. Okay, why? Because that depends on what fiber we are considering. If you are considering the outside, then that will be C, where I denotes the force moment of inertia from the neutral axis or with respect to the neutral axis. And then your bending stress, if you will try to proceed with your B, section BB, movement, just move a little bit, okay? That M will become M plus dm, okay? So that will now be our stress. Instead of having the M, that will now change with M plus your differential moment. And then of course, if you want, okay, we can now multiply the area to the stress for us to convert that one into a force. Okay, so look at this. Let us now consider an equilibrium of the shaded element ACDB. So this is the element that we are trying to investigate, ACDB. So this rectangular here. So that is the side view and this is the cross-sectional view. Okay, the force acting on the area dA, okay, this is your differential area of the face AC, okay, this is your face AC, is merely the product of the intensity of the force and the area. Okay, so again, if you want to consider, since this is our shaded area that or shaded element that we will be analyzing to derive the relationship, then if you want to convert this pressure into a force, all we need to do is multiply the pressure by the receiving area. Since again it says there that the phase AC is what we are going to consider, so what we are going to do, let's say that is the differential area. This is your differential area. Multiply that one with the stress to make it as the force. Okay, so that is your transformation. So isn't it your stress is my over I? Multiply that one to dA, so you have your dA on this side. The sum of all such forces over the left face AC is found by the integration. So again, for us to get now the whole, this is a differential force, of course, due to that dA. Your area is small, so that your force is also small. So if you want to get the total force, all you need to do is apply integration, of course, since that is a differential. So apply integration, you will have now your side as integral of my over I times dA. We need to consider the limit, since let's say this is the element that is under consideration, so we will only summate from y. Okay, we are integrating, your variable here is y. Okay, your variable here there is y, so we will try to integrate from y equals y, that is itself here, to y equals c, since we are considering this element. So that is how we are going to integrate to summate to get the entire force acting on your AC, since again this is just your small force, the differential F. So likewise, the same thing on the other side, BD, okay, in this other side, BD, that is the same thing, but this time your moment will become M plus dm, okay. So to make that one force, concentrated force, all you need to do is multiply that one with the differential area, so that you will make this one as a concentrated force on the side BD. And then of course to maintain equilibrium, okay, to maintain equilibrium, that To maintain equilibrium, as you can see, this force here is due to the moment, and the force here on the side BD is due to M plus dm. So let's say that this differential of moment or the change in moment is a positive, so this will be bigger compared to this M. Therefore, if I will convert the concentrated force in your AC compared to your concentrated force at your BD, since that is bigger, the force here is bigger compared to this. Therefore, let's try to say that to make it equilibrium, summation of horizontal should be 0. Therefore, if this is smaller, the concentrated here is smaller than the concentrated there should be a reaction that will help that one to make it equal. So, if you will try to look at this, the area which is in your plane CD will try to help through friction. Okay, through friction, that area will try to resist together with the force here in your AC to make it equal with the concentrated force in your BD. So we have this shearing force or shearing stress, which let's call that one as tau, okay, to resist the additional or the extra or the resultant force if you will try to summate to make it equilibrium. So let's denote that one as tau, since of course that is a shear, and we discussed that one on the previous module, of course. Okay, to denote the shearing stress, let's to differentiate that with the axial, let's make let's use the tau. Okay, so now okay, this is what I'm explaining a while ago. So this one is the concentrated force in your AC. We derived that one a while ago. This one, to make it the concentrated force, that is integral of my over IdA. On the other side here will be, this will just change to M plus dm. But to resist that one, to make it equal, let's try to add the shearing resistance here, or the shearing stress, which is to be converted into a force. Okay, we will convert this one into a force since we are summating forces. So this is a shearing stress. To make it force, multiply by the receiving area. So what is the area? This is the side of that CD, and then multiply that one with the cross-sectional dimension, which is B. So what is this distance CD? Let's say that that is dx, since that is our assumption a while ago. Okay, so to make this one force, tau will become times multiply that one with the area B times your length dx. So that is the area of this. Okay, receiving your or resisting your tau. So again, look at this, positive, since let's say going to the right is positive. So this due to M force in your AC is going to the right, and that force due to the shear is going to the right. So they are positive, and that due to M plus dm is a negative. So to make it equal, okay, to make it equilibrium, equate that one to 0. Then actually look at this, you can break this down. So you can make that minus integral of mi dA multiplied to y, and then separate the negative dm, integral of dm iy, and then dA. So look at this, you will bring out something like that equal to this, which will cancel a negative, so that will cancel totally. So you are left here with a negative dmy over ida. Then all you need to do is transfer that on the other side, and then what will be left here is this one, and then play around, cross multiply this below. You will end up with the equation of your tau, which will be 1 over IB times dm dx, the integral of y dA. Okay, so that is our tau. Then if you'll now try to recall our relationship of the load, shear, and moment in your module 4, okay, according to our derivation there, your differential of moment with respect to x, or with respect to the length, the first derivative of that is actually the slope, or that is corresponding to the intensity of the shear, isn't it? Again, recall your module 4, or if you cannot recall, go back to the module 4. We derived that the slope of the moment, or the first derivative of the moment, is the intensity of the shear. Okay, in your equation here, therefore we can change that one into a shear V. So that will be simplified as V over IB integral of y dA. Okay, again, what will be that V? That is actually the shear which is experienced by this cross section. Okay, you might be saying, why is it that we are considering two cross section and you are only considering one? Since again, The differential means that is a very, very small. So later on, the change in shear from this section to that is very, very small. So let's assume, okay, that is almost equal. So, okay, we will consider one section, and that is the shear at that section. That is the internal shear. Okay, you can get that one in the shear diagram, or you can use the shear equation. So again, we are now simplifying this into your b over ib integral of y dA. Okay, still from y to c, since we are considering this element. Okay, however, we can replace this one, which means that this is the sum of the first moment of differential areas about the neutral axis by y prime y bar. So if you'll try to look at this in your flexural stress, that is y squared times dA. So that is a second moment of area. So that is relating to your I, but in here that is just y times dA. That is the first moment of area. Okay, so that is not I. So let's just, okay, the meaning of integration again is to summate. dA, of course, dA there are the differential area somewhere here, and we are going to take the moment of that with respect to the neutral axis. So if I will try to do that, summate that one, okay, only one side, of course, focus on the one side. It could be the top or below. Do not combine the two, because of course that should be 0. Okay, so for us not to cancel the equation, do not summate the entire. Okay, we will just be summating. Look at this. That is the reason why we are applying this limit. Okay, so a prime times the y bar. A prime there is the area of the part that we are considering, and then the y bar there is the centroidal distance to your neutral axis. Okay, so again, a prime is the partial area of the section above or below, whichever is easier to compute. By the way, I will explain this one. Why is it that we can consider the top or below? Okay, I will show you that by example later on. They will be giving us the same value, so we will only be considering one of that. It depends, whichever is easier to compute. Again, your y there is the moment arm of the area with respect to the neutral axis. So that is, of course, the moment arm is on the centroid of the area we are considering. Okay, so a variation of product a prime y bar is the symbol q. In other formulas or in other books, they use that instead of a prime y bar, they are using this q, which means that is the static moment of area, or that means they are going to summate the moment, or this one. Okay, they are going to summate that one, and they will represent that one as one variable q. Okay, so that could also be the formula. Instead of y prime y bar, a prime y bar, you can change that one to q, if that is how you want to solve it as a whole. So if you are considering your q as a single quantity, then look at this, area times a distance, so you will expect there a cubic units. Okay, so now, okay, it's up to you. Again, you can use this, or you can change that one to q. So again, these are the definition. Okay, these are your definition. The tau there is the horizontal shearing stress, which is experienced in your plane area parallel to the axis of the beam. Okay, it is not the vertical. Okay, it is not the vertical. It is in your what we call this one, grains, or it is in the fiber parallel, or the surface area, or the area parallel to your axis of the beam. So in your formula, look at this. Your y bar is actually the distance from the neutral axis. So let's say if you want to consider this area, the y bar of that is different if you want to consider the entire area on top of the neutral axis. The y bar of that is different. So your y bar is actually the variable that affects the shearing stress. Okay, so look at this. If you want to consider this area, this is where the shearing stress is experienced. If you want to consider a little bit below, the y bar will be smaller. Okay, the y bar will be smaller because the centroid will be going down a little bit. So let's say somewhere here. So your y bar will be smaller. So look at the formula. If that is smaller, your shear will be smaller. So same thing as bending or your flexural stress. Your horizontal shearing stress is also proportional with respect to the distance of that plane that we are considering with respect to the neutral axis. So as we go, okay, as we go further, as we go away that neutral axis, the horizontal shearing stress is what we call this one is changing. Okay, imagine this. Imagine the entire. Okay, I will consider. Let's say I will consider up to your neutral axis. Okay, I will consider up to your neutral axis. You will have there a smaller y bar, but the area is bigger. Compared to, I will consider almost, okay, almost very small, close to your extreme fiber here. You have a big y bar, but the question there, the area is very small. So what does that mean? It will be the reverse. Your bending moment is increasing as we go away the neutral axis, but for shearing stress, it is decreasing as we go away the neutral axis. Since again, the area, it is not only just your y bar that changes, it will also be your a prime. Okay, so even as we go away the neutral axis, your y bar is increasing, but your area is decreasing. And which one affects more, the distance or the area? Of course, your area, since area is multiplied. Okay, these are two quantities multiplied together. Okay, and then of course your y bar is just a single quantity. So your area affects more the stress than the distance. So, okay, you can prove that one if you want. You can prove that one. You can consider a small distance here or a small area here, considering or compare that one to considering the entire area on top of the neutral axis. You will find out that the shearing stress, that tau, that we will be experiencing within your neutral axis is bigger than that farther from the neutral axis. Okay, so that is for horizontal shearing stress. But okay, for composite cross section, okay, for composite sections of figures, the question there, this is derived in your, this is for plane rectangular. But the question, isn't it just like in your flexural, if we will end up there with an I shape, okay, and then the I is not symmetrical with respect to the neutral axis, then what does that mean? The C on top and below are different. And of course, the areas will be different. So what will happen there? Okay, your A prime bar, A prime y bar will be changed to summation of A prime y bar of each of the areas. If you will, let's say this is I, you need to break this down into areas. Then that A prime bar, you can change that one to summation. Okay, all you need to do is summate all the areas that you subdivided, the product of that A prime and their y bar. Okay, each of the area that you subdivided, summate that one, and that is your Q. Okay, the Q of our formula. So, okay, let's have an example for this. So we have here your plane. This is plane rectangular. We have here plane rectangular. So again, your formula is this. So all we need to do is find, okay, the question there is find the maximum horizontal shearing stress at the neutral axis. Again, that's why I explained you, we will be a while ago that we will be having our maximum horizontal shearing at the neutral axis, because the area, if you are considering the entire part on the top of the neutral axis, the area is bigger compared to the area if you will just consider a small area there which is close to your extreme fiber. Okay, so that is where we will find the maximum on your neutral axis. So, however, in your formula you need the V. So for us to get the maximum shearing stress, we need to consider the cross section within this length where we can find that maximum shear. And of course, you can see that one if you try to draw your shear and moment diagram or your shear diagram, because that is what we need. Okay. In your flexural stress, what we need is your moment diagram, but in your horizontal shearing stress, what we need is your shear diagram. So, according to our example before, in your module 4, this is an example before on that module. This is the shear diagram. So, the maximum, okay, by the way, in this one, in horizontal shearing stress, unlike in flexural, that we need to investigate. If there is a maximum on the positive and maximum on the negative, we need to investigate that. Because again, especially if your neutral axis is not exactly on the middle due to unsymmetrical property of that section. So maybe even if that is a bigger number compared to this, that might end up with different effect. This could be giving us the maximum bending if that is in bending, because again the bending actually depends on the curvature. The bending stress depends on the curvature, which one is compression and tension. But in shearing stress, it doesn't matter. Okay, in horizontal shearing stress, it doesn't matter if that is a positive shearing or that is a negative shearing, because we are still investigating your neutral axis. So even considering your top or below, that will, even if they have different C or distance of the extreme fiber, still the area on top and below should be, the moment of the area should be equal. Okay, because that is how we calculated your Y bar, satisfying that the moment of area, okay, of the top and bottom or of the entire should be equal. Okay, so that is how we calculated your Y bar. Therefore, it means that if I will try to take the moment of area of the top with respect to NA and then the below with respect to NA, they should be equal. I will show you that one in this example. Okay, I will show you that one, or on the next example, because in here it is obvious. Okay, since the C here is just half of the height, then it's either using the below or top that will give us the same. Okay, so that will give us the same. Therefore, in here, I will be using, instead of considering the two, all I need to do is look at the bigger value, even if that is a positive or negative. Just consider the absolute, the maximum of the absolute value of the diagram. So that is 17, so that is what we will be using. Even if you try to use this one, that will give us smaller than 17. Okay, so your V maximum to give us the horizontal shearing stress, which is maximum at neutral axis, will be that 17. Then, of course, your I and A the same. We will be getting the I with respect to the neutral axis. That is a rectangle, so 1 over 12 BH cubed. So that will be 1.33. We had that one before, since this is an example of your flexural stress. Your B there, actually, okay, going back to this definition, your B is the width of the layer at which the shearing is being computed. That is the width where the shear is being evaluated. We are getting the NA, the shear at the NA. So that is the width of the beam at your NA. Let's say this is an I shape. Later on, the width on top and the width on the NA will be different. But still, the B should be on the cross section or on the width on the layer that we are considering. And again, we are getting the maximum at the neutral axis, so that should be the B, the width of your beam at the neutral axis. So that is 250, since that is uniform. Okay, and then your area there, okay, we will consider the entire here. Okay, look at this. If you want, you can consider the area on top, and then of course multiply that one with its Y bar. That should be the same below, because it is symmetrical, vertical and horizontal. So no problem with rectangular, you can consider any. And actually later on we will be having an I, which is our example also in your bending. So you can see the difference. Okay, so A prime, let's consider the top. That is 250 times 200. Okay, that will give us 50,000. Okay, 50,000 millimeter squared. And then your Y bar there is 200, half of your height, which will be 100. So we need to resubstitute. Okay, Vmax is 17 times 10 raised to 3 to make it Newton. Your I is millimeter 4. That B there is the dimension, which is still 250. And then the area, okay, area prime, that is the area of one side of the neutral axis. You can consider below if you want. Okay, and then the Y bar there is 100. And then that will give us 0.255 megapascal. So that is the shearing, maximum horizontal shearing stress, which is found in your neutral axis at this point, which is at exactly on the support. Okay, at the support, that is where we will find the maximum shearing stress. Okay, now let's try to have another example. Okay, example number 2. This time the beam which we analyze in the second example of flexure. So this time it is now in unsymmetrical I section. So again, we established the I of this before, so I will not repeat again the process how to get the I. And then of course your Y bar. Okay, so go back to that module to that unit, which is your unit 1 of module 5. To again, if you want to recall how we get your Y bar and the I. of this. So again, maximum horizontal shearing, which is also again found in the neutral axis. The maximum horizontal shearing is always found on the neutral axis. Okay. So look at this. The B here now is different from the B in your top and below. In your flanges, we call that one the flange. This is the web of the eye section. Okay, so still consider this width where we are analyzing, which is your neutral axis. So that your B here is, our B here is your 10, which is the dimension. However, we need to find the maximum shear. Again, draw the shear moment diagram, use the shear diagram, and again, look at the absolute maximum. It could be a negative or positive, and that is your 14, which is found in your at your support at point B. Okay, so that is what we will be using. So now, okay, look at this. A while ago in your rectangular, I did not show you the difference of using the top and below, because of course it is obvious that they should be equal since that is symmetrical. But in here, okay, let me show you. Okay, let me prove to you that using the top or below will give us the same. Okay, using the top. Okay, look at this. Using the top, the area. Okay, by the way, we get the we established before that the y bar is 50 from your base and then 70 from the top, and of course that 60 is on the centroid, that 40 is on the centroid of the rectangle. And of course, if that is 50 going here, and then of course minus that 20, the remaining is 30. So half of that to get the centroid of this rectangle here is 15. And again, if that is 70, subtract your 20, the remaining will be 50 divided by 2, that is 25. Okay, so you have already the dimensions here in the figure. Okay, focus on the top. Okay, let me prove to you that this will be the same. So again, instead of a prime y bar, we need to summate all of the areas. Since again, I need to divide this, I cannot do it once. Unless, of course, unless you will find the centroid of this two area, the combination centroid of that, as a total area or as a single area with respect to NA. You can do that. But instead of doing that, it will be faster to just summate this A area times the y bar. So the area of the top is 60 times 20. Multiply that one with the y bar from the neutral axis, which is 60. Plus the second is 10 times 50. And then y bar of that is 25. It will be giving us 84,500 millimeter cube. Okay, you can consider this as your Q. In the other formula of other books, they are using this as Q. They are using a Q variable. Okay, below, let's try to do the same. Get the moment of area. So in this area, that is 20 times 100. Moment arm of that is 40. And then in here is 10 times 30. Moment arm is 15. So that will be giving us exactly the same 84,500, which is again, okay, comparing the upper and the lower of the neutral axis, that will be giving us the same. So that's why in the note here on our derivation is for you to consider which one will be easier to be calculated. Okay, A prime, it's up to you if you will consider the above or below, whichever is easier to compute. Because there are other composite members wherein the shape on the top is a little bit complicated to the below. Just like, for example, let's say this is a T section. If we say T, that is in the form of T. So if I will try to cut somewhere there on the neutral axis, we do not have this. That is only just a rectangle if that is a T section. So for me, it is simpler to solve the area of the below and get the moment, the first moment of area. Again, it's up to you, whichever is easier. But you can use the both to check the other one. Okay, so that is our summation. Since again, this is composite, so we are doing summation. But if that is the simple rectangle, then only one, A prime times y bar. So we already have that. Your INA, by the way, we solved this one in your unit 1. So go back there if you want to recall how we ended up with that INA. This is, we solved this one by the transformed moment of inertia. So that is the summation of I plus AD squared. Okay. So now we are complete with your variables. Substitute. Vmax is 14. This one. And then make that Newton times 10 raised to 3. Your I is 8.133 times 10 raised to 6 millimeter for your B there again. Okay, I will emphasize this one. The B is the thickness, or that is the width of the beam on the surface that we are considering, and that is the neutral axis, so that is the B, which is 10. And then of course this is what we solved a while ago, summation of your area times centroidal distance, which is the first moment of area. Okay, substitute, calculate, that is 14.55 megapascal. So that is your maximum horizontal shearing, which is found on your neutral axis at point B of our entire beam. Okay, so that's it. That is for horizontal shearing stress. If you have any question, you can comment that one below the video, or we will discuss that one on our live meeting. So thank you very much for watching.